So I just got this comment today. He says, can you show that in a group G, if A squared is equal to 1 for every A in G, then GH is equal to HG for every GH in G? This is an abstract algebra question, and this is going to be the first abstract algebra question that I'm doing on my channel, and it's also the first abstract algebra question that I'm doing in like 14 years. So let's see if I can really do this or not. Right here, we have G being a group, so let me just give you guys an example to see what this means. So let's take a look at the set of all the integers, which is denoted by Z. In order to talk about the groups, we have to have a set and an operation. Let's say we want to talk about the addition operation. Right here, the main thing that we'll be using for this question is that you need to understand the idea that Z is closed under addition. Just like when you have a group, it's going to be closed under whatever the operation that you have. Right here, you can just think about this right here as G times H, like a multiplication. Usually you can put like a little star as like an operation that we're doing, but you can also ignore that, which is just like this. But what do we mean by closed under the operation though? If you have Z and addition, then you can pick any two elements in Z and then add them up. You'll still end up with an element inside of this set. So let's say if you have 3, which is an integer, and then likewise 5 is also an integer, and if today you add them up, 3 plus 5 is 8, and of course that is still an integer. So we say that the integers are closed under the addition. But isn't this all like the case for all the operation that you can think about? Well, it depends on what kind of set that you're talking about, and also the operation. Right here, if you're talking about the set of all the natural numbers, let's say this is just a set of all the positive integers. And if you want to use subtraction, then this is not closed anymore. Because for example, I can say 3 is a natural number, 5 is also a natural number. But if you have 3 minus 5, which is -2, this right here is no longer a natural number, because natural numbers, we do not include the negative integers. So this is not going to work. And this is the idea that we will have to use for this question. Okay, here we go. Firstly, because we are writing a proof, we should start off by writing down PF for the proof. And I remember the good old days. That was the only thing I was able to write on many exam questions. But anyways, well, we have G being a group already, and then we have this assumption, and this is what we're trying to show for all G and H in G. So these are just two elements in the group G. So we should start off by saying, let G and H be any two elements in G, and that will be enough. Now, because G is a group, so what do we know? Well, that's the idea I gave you guys earlier. We are going to do the operation with these two elements, and we know the result will still be in the group G. Therefore, I'm just going to use arrow. I will just say this implies GH is going to be inside of G, because G is a group which is closed under its operation. Okay, now what though? Well, we have an element in G. Therefore, we know that by this assumption, for every element in G, we know when you square that, we just get 1. And 1 is just the identity element. Sometimes you can use E, but here we are using 1. So, okay. Therefore, we can say GH, if we square that, we are going to get 1. Then for the squared, we can do the usual business. We can write this as GH times GH. Right, just write it down twice, and then we still end up with 1. Now, one of the things that we can do right here is that we can get rid of the parentheses, because we can say by the associative property, right? Just like the parentheses doesn't matter. However, one thing that we cannot do is just switch the order of G and H, because that's what we're trying to show. GH is equal to HG. And when this happens, this means the group G is abelian, meaning all the elements inside are commutative. you can switch the order. But anyways though, right here, let's take a look at GH is equal to 1. What can we do next though? We have GH here. I kind of want to somehow turn the order and then get HG, then we can finish, right? And this is how we can make that happen. Remember, we have this to use. Right here, A squared is equal to 1. All the way in the front, we have G, and remember the order matters. I'm going to go here, all the way in the front, multiply by G, and of course I have to do the same thing on the right hand side. Now, I can put them like this. Remember, we can group the elements and then do whatever the operation that you want. So if you look at this, we have G squared. And by this again, we know that's equal to 1. So we can say 1 and then just think about this as multiplication. But that's that G and then times 1, something like that. Well, this is going to give us GHG is equal to G. Okay, now what? Well, we can do the same thing, right? All the way in the front here, we have H. So let's just go ahead and multiply this by H and do the same thing right here. Again, the order matters. If you do this all the way in the front, you also have to do this all the way in the front. And then look at this. H squared. H is an element of G, so of course when you square that, you get 1 again. And then GH is equal to HG. This is just an identity element. When you do this to that, doesn't matter. So there you have it. We get GH is equal to HG. Therefore, we are done. Just like that. Yep.